Welcome mathematicians to this video on probability tree diagrams. You have in front of you a sample of a probability tree diagram. It's a visual way of looking at probability with sequence of events. So let's jump into it. So first up, let's look at a simple coin toss where we have two options and each outcome is equally likely. So first of all, we can toss a coin and there's a 50% chance we'll get a head and a 50% chance we'll get a tail on our first toss. If we do this again a second time, we could get again a 50% chance for head again and a 50% chance of a tail. And that would be repeated for the second branch as well. So here's the four possibilities after two tosses of a coin. So the sample space, which represents all the possible outcomes. We could get two heads. We could get a head for the first toss and a tail for the second. Or we could get a tail for the first toss and a head for the second. Or we could get two tails. Quick question, what's the probability of two heads? So the probability of two heads is represented by the number of times we can get two heads compared to all possible outcomes. So two heads here is a 1 out of 4 chance. So the probability of tossing two heads in a row is 1 in 4. Question number 2, what's the probability of throwing one head and a tail in no particular order? So the chance of this is we're looking for what particular outcomes in a sample space represent one head and one tail. There's one and there's one. Divided by all the possible outcomes. So there's two ways in which we can throw one head and one tail. It could be a head and a tail, or it could be a tail and a head. And there's out of 4 outcomes. So 2 out of 4 is a probability of a half. Question number 3, what's the probability of throwing one or more heads? Well, we can see that there's 1, 2, 3 ways in which we can throw one or more heads out of 4 possible outcomes. So the probability of throwing one or more heads is 3 on 4, 3/4. The individual probability of a double head can be easily calculated also by multiplying the probabilities of each of these particular branches. So there's a 50% chance, a 1/2 chance on the first toss of getting a head, and then another half chance of getting a head in the second toss. So if I multiply those together, I end up with the probability of two heads is 1 on 4. Also, the probability of getting a head first then a tail, it also is a 1 on 4. Likewise, the probability of getting a tail then a head is 1 on 4, as is the probability of getting two tails. When we add each of these individual probabilities together, we end up with 4 on 4 or 1, which represents 100% certainty that one of these 4 events will occur. If we went to a third toss, you can see that increases our sample space from 4 outcomes to 8 outcomes. And that also means that our probability is a half times a half times a half, which is 1/8. And that's the same for all the 8 different outcomes. Again, the total of these 8 different outcomes of 1/8 gives us 8 on 8 or 1. Let's now look at a three-way spinner. And we have 1, 2, 3 options. It could land on the blue, green or red, and each is equally likely. So let's have a look. We spin it our first time and we get a 1 in 3 chance it could be a blue. Spin it again. There is also a 1 in 3 chance it could be a red. And finally, there is a 1 in 3 chance it could be a green. If I was to repeat that spin again, I've got a 1 in 3 chance for blue, another 1 in 3 chance for red, another 1 in 3 chance of a green. They're all equally likely. And that would be repeated again. So there's all the possibilities for 2 spins of a three-way spinner. So our sample space again, all the possible combinations going from 2 blues right through to 2 greens. So the questions we could be given. Example number 1. What's the probability of 2 greens? Well, we can see here that I've got 1 double green out of a possible 9 outcomes. So it's a 1 in 9 chance. What's the probability of 2 of the same color? So you can see that I've got 2 blues, 2 reds, 2 greens. That's 3 particular outcomes out of a total of 9. So that gives me a 1 on 3 or a third probability. What's the probability of not getting red? Well, I can easily work out all the options here without red, 1, 2, 3, 4, and divide that by 9. And that will give me an answer of 4/9. Another way I could have done this was to look at the probability of not getting reds would be 1 take the probability of getting reds, because there's 1, 2, 3, 4, 5 ways in which you can get reds. 5 on 9, 1 take 5 on 9 gives me 4 on 9. And again, the individual probabilities for each outcome in the sample space, there's a 1 on 3 on the first spin of a blue, plus another 1 on 3. So when I multiply those two together, I end up with 1 on 9 probability of getting 2 blues. And that's the same equally probable outcome for each of those 9 possibilities. Again, when we add them all together, we get 9 on 9, which gives us a 100% probability. Let's now look at a 4-option equal likelihood probability distribution. So we have here a deck of playing cards, and we know that cards come in the suits of a spade, heart, club, and diamond. So let's look at the probability of picking a particular suit from a standard 52 card deck. So we have a 1 in 4 chance of selecting a spade. Equally, we have a 1 in 4 chance of selecting a heart. We have a 1 in 4 chance also of selecting a club. And finally, you guessed it, a 1 in 4 chance of selecting a diamond. Now, when we add those 4 possibilities up, 1, 2, 3, 4, 4 1 in 4s or 4 quarters give us a whole of 1, which makes sense. They complement to a value of 1. Now, if we were to repeat this, of course, we'd have all of these various options in our sample space representing the 16 possible combinations of suits if we picked one card, then a second card, ranging from a pair of spades right through to a pair of diamonds. Question number 1. What is the probability of selecting a pair of suits from this 2-pick option from a deck of cards? Well, let's have a look at the number of pair of suits we have. 1, 2, 3, 4 options. Pair of spades, pair of hearts, pair of clubs, and pair of diamonds. And we compare that now to a total sample space of 16 outcomes. So 4 and 16 can be simplified to 1 and 4. There's a 1 in 4 probability of selecting a pair of suited cards. Question 2, what's the probability of selecting at least one black card when I select 2 in a row? So the probability of at least one black is the number of at least one black pair divided by the total outcomes. So we've got a whopping 12 combinations here that have at least one black card in them. Okay, so 12 out of 16. That gives me the probability of selecting at least one black card when I pick 2 successive cards is 3 quarters or 3 on 4. In order to get 2 spades, there's a 1 in 4 chance in the first pick and another 1 in 4 chance in the second pick. If I multiply those together, I get a 1 in 16 chance. And that's the probability of all those particular outcomes. And again, those 16 options, when multiplied by 1/16, give me a probability of 1. There's certainty that one of those combinations will come out when you pick 2 cards. Let's have a look now at 2 options with unequal likelihood with replacement. So let's have a look at this. Pick number 1. We have here a container with 1, 2, 3, 4, 5, 6, 7, 8, 9 balls. 4 of them are blue and 5 of them are red. So if I pick one, the likelihood of getting a red ball is 5 in 9. There were 5 reds out of the total of 9. Or alternatively, the likelihood of picking a blue ball was 1, 2, 3, 4 out of 9. Notice those odds have to add up to 1, 9 out of 9. They complement each other. Pick number 2. With putting these balls back where we started with replacement, we do this again. The chance of picking a red ball is again 5 out of 9. And the chance of picking a blue ball is 1, 2, 3, 4 out of 9. Likelihood again of starting with the first pick was a blue. We've got the next pick is a red, will be 5 out of 9. And finally, again, second pick being a blue is 4 out of 9. So here's our sample space, double red, a red and a blue and a red and a double blue. Now these probabilities are not equally weighted. They're not equal numbers at the start of the blues and reds. They're unbalanced. So this is an unequal likelihood. So if we multiply 5 ninths by 5 ninths, multiply our numerator at the top, 5 by 5 is 25, and multiply our denominator, 9 nines are 81, we've got a 25 in 81 chance of picking 2 reds. If I look at the chance of picking a red on the first pick, and then the second pick we get a blue, I've got a 5 on 9 chance for the first option, and then multiply that by a 4 on 9 chance of getting a blue. That's 20 on 81. The same again, if I select a blue on the first ball, there's a 4 on 9 chance, and a red on the second ball, there's a 5 on 9 chance. I get a total probability of picking a blue then a red. By multiplying those individual probabilities, I have 20 out of 81. And finally, the chance of getting 2 blues. The first pick was a 4 on 9 and the second pick was a 4 on 9. Multiplying the top 2 4s are 16 and 2 9s are 81. So there's the probability of each of our outcomes in our sample space. Again, if we add all those fractions together, we get a total of 81 out of 81. There's a 100% certainty that one of these probabilities will occur. Question 1. What's the probability of selecting 2 different coloured balls? So we could have picked a red and a blue, and we could have picked a blue and a red. When I add those 2 individual probabilities together, that gives me a probability of 40 over 81. So the probability of picking 2 different coloured balls out of 2 picks when I'm replacing these balls back after each selection is 40 out of 81. Finally, let's repeat this process without replacement. So pick number 1. Again, we have 1, 2, 3, 4, 5 chances out of 9 of picking a red ball. And if we were to take that out and not replace it, let's pick again. What's the probability of picking another red? I've got 1, 2, 3, 4 out of 8 now. So I've gone from 5 out of 9 on the first pick to 4 out of 8 on the second pick. Alternatively, I could have had a second pick and selected a blue ball. Now I've got 1, 2, 3, 4 out of 8. So there's a 4 out of 8 chance of a blue as well on the second pick. Let's go back right to the start. Instead of a red, let's say I picked a blue. I've got a 1, 2, 3, 4 out of 9 chance of picking a blue. And again, these numbers here complement to give me 9 out of 9, a complete probability of 1. I've taken that ball out. I've not replaced it, and I'm going to select a red this time. So I've now got 1, 2, 3, 4, 5 out of 8, a 5 out of 8 chance of picking a red. Or if I put it back and instead of picking a red, I picked a blue, I've got a 1, 2, 3 out of 8 chance. I've got a 3 out of 8 chance of picking a blue on the second pick without replacing the original pick. Let's look at the sample space. So the 4 possible combinations of these red and blue balls without replacement is 2 reds, a red and a blue and a red, and a blue and a blue. Let's look at the probabilities. If I go across the top red line here, I find I have a 5 in 9 chance of selecting a red ball on my first pick and a 4 in 8 chance of selecting a red ball on the second pick without replacement. So when I multiply these two fractions, I get a 20 on 72 chance or probability of picking 2 reds. The probability of picking a red on the first is a 5 on 9 chance, and the probability of picking a blue on the second is a 4 on 8 chance. So the probability of that two combinations, a red ball first and a blue ball second, without replacement, is the product of these two individual probabilities. It's also 20 out of 72. Likewise, selecting a blue, then a red, is a 4 on 9 by a 5 by 8, which is a 20 out of 72 also. And finally, the probability of selecting 2 blue balls in a row without replacement will be a 4 on 9 multiplied by a 3 on 8. When I multiply those together, I get a 12 on 72. No surprises, when I add these 4 fractions together, I end up with a 72 out of 72, which is a 100% probability that one of these options will occur. So our final question, what's the probability of picking 2 balls of the same color without replacement? So first of all, let's have a look at the 2 options where we do have the same color. I've got 2 red balls and 2 blue balls. So working out the probability of selecting 2 balls of the same color without replacement is found by adding these 2 individual probabilities together. So the first one, 2 reds, was a 20 on 72 chance or probability, and the second option, the 2 blues, was a 12 on 72 probability. When I add them together, I get 32 on 72. So the probability of selecting 2 balls of the same color without replacement after each pick is 4 on 9. Thank you for watching this video on tree diagrams. I hope the analogies and the examples presented have helped you understand the concept a little clearer. If you've enjoyed this video, please like, share, comment, and subscribe. And as always, thanks for watching.